For 6.7, we have to review this formula, y equals a sub 0 e to the kt. Now in this formula, I may sometimes write a of t equals a sub 0 e to the rt. Sometimes I may write a equals a sub 0 e to the rt. These are the formulas that I know, but they work the same way. We just use different letters than the textbook does. Okay, now in this formula, this part is always the final amount after so much time has passed. This is the original amount, this is your rate of decay, and this is your time. Alright, so we need to get a couple of definitions. The doubling time is the time it takes for the quantity to double. So if you started out with 1 gram, that would go here, and you want it to double, that 2 would go here because 2 is double that 1. Okay, so what is half-life? Half-life is the time it takes for a substance to exponentially decay to half of its original quantity. So if we talk about half-life, let's say our original amount was 1 gram. Well, for the half-life, that means half of it will decay. So the original amount is 1, but the final amount would just be 1/2 or 0.5. Alright, so let's look at an example. The half-life of carbon-14 is 5,730 years. Express the amount of carbon-14 remaining as a function of time t. Alright, well, they want a function. They're not asking us to solve anything. They just need an equation. So before we can do that, we have to figure out what our rate of decay is. So we know that the half-life is 5,730 years. That means if we start with 1 gram, when the half-life is reached, we have half a gram, right? So that's what we go with. We have half a gram remaining, starting with 1 gram, e to the r, which we don't know, and t is 5,730 years. It takes this long for 1 gram to be reduced to half a gram. It's very important that you know how to set up this equation. So this becomes 0.5 equals e to the 5,730 r. Well, now we just have to solve the equation. Just like in the last section, we're going to take the natural log of both sides. So we have the natural log of 0.5 equals, we can use our power rule since we have a logarithm. So 5,730 r natural log of e. Remember that the natural log of e is 1. So you have 5,730 times r. Divide both sides by that number. So r will be something like, let's see what kind of number we get when we calculate this. We get this kind of ugly number, right? So if we're trying to write a formula, we definitely don't want to round the number. I'm going to write it down anyway, just so you'll have it on your paper. Negative 1.21 times 10 to the negative 4. What we want to do though is keep it in this form. The natural log of 0.5 over 5,730. Because what we're trying to do is actually write that equation. Remember your formula, a equals a sub 0 e to the rt, right? Or a of t if you want to think of it that way. So we have our final amount is equal to our original amount, e to the, this is your r, natural log of 0.5 over 5,730 times time. So if you wanted to take some substance that you know the original amount of and how long it's been there, you can find out how much is left. So this is going to be your final formula for that problem. Okay, we're going to use the information we just gained to solve this next problem. A bone fragment is found that contains 20% of its original carbon-14. To the nearest year, how old is the bone? So remember, this is carbon dating. So we're basing all of this on the science behind carbon dating. So we know that it has 20% of its original amount. Well, the original amount was 100%, right? 20% is 0.2, and 100% would be 1. So when you're putting all of this into your formula, the final amount is 0.2, the original amount is 1, e to the, your r is what we just found in the previous problem. We're filling everything into this formula. So natural log of 0.5 over 5,730. And we're actually looking for time. We want to know how old this bone is. So to solve this, we need to take the natural log of both sides. Remember that 1 is just 1 times all that, so we don't really need it sitting there. So we have natural log of 0.2 is equal to, bring the exponent down, the natural log of e is 1. So we divide by all of that stuff. Now these will go away. We're left with our t is equal to something. We want to know how old this is to the nearest year. So let's put this in the calculator and see what happens. We have natural log of 0.2 divided by, I'm going to put this whole denominator in parentheses. So natural log of 0.5 divided by 5730 and close the denominator. And we get this number, 13,305, because it said the nearest year. So what does that mean? That means this bone is approximately 13,305 years old. All right, last one. According to Moore's law, the double time for the number of transistors that can be put on a computer chip is approximately 2 years. Give a function that describes this behavior. So again, it says give a function. That just means write an equation. Our basic equation is a equals a sub 0 e to the rt. It says double time is approximately 2 years. So if we start with 1, double would be 2. So let's do that first. 2 is equal to 1 e to the r, and t, it takes 2 years for it to double, right? So that's just 2. Now we need to solve that. Let me make it look a little better. 2 is equal to 1 times all that, so e to the r times 2 is 2r. We can take the natural log of both sides. So we have the natural log of 2 is equal to, bring the exponent down, natural log of e is 1, divide both sides by 2. So r is equal to the natural log of 2 divided by 2. Now we're trying to find the equation, which means it needs to look something like this. So our final amount is equal to our original amount, e to the r, which is natural log of 2 divided by 2, times t. This is our function.